In this video, we are going to talk about advanced topics about learning the MAC addresses. We are going to explore how the switches learn the MAC addresses. We are going to observe them learning this using show and debug commands. Then we are going to talk a little bit more about the MAC address table, how we can query the information in there, how we can clear the information, how we can statically put the information in the MAC address table. And finally, we are going to talk about the life of the frame in the switch. What happens with the frame when it arrives on one port and before it is sent to other ports? Which processes on the switch does this frame undergo? So let's go and take a look at this. What I'm going to do is I'm going to set up a very simple network. This very simple network is going to be consisting of a single switch, which is going to be my Cat1. So here it is, my Cat1. I'm going to have two routers connected to Cat1. I'm going to have router 1 and I'm going to have router 2. On router 1, I'm going to be using fast Ethernet 00. On R2, I will be using gigabit Ethernet 00. This is going to be connected to fast Ethernet 01 on Cat1 and on fast Ethernet 02 on Cat1. What I'm going to do here is I'm just quickly going to go and set this up. Just a very, very basic setup. And let's see if I can communicate between R1 and R2. So I'm going to go to my terminal here. And I have here three tabs. I have my Cat1, I have my R1, and I have my R2. This is the configuration on the fast Ethernet 01, and this is the configuration on fast Ethernet 02. You can see here that I have enabled a feature called spanning tree port fast. I will talk about this feature more when I talk about the spanning tree advanced features, but for now, the only thing that I really care about, the reason why I configured this feature, is that I don't want to wait for certain spanning tree processes, the learning and the listening phase on the port when the ports initially come up. All I want to do now is to test the basic functionality of the switch. I don't really want to be concerned about the spanning tree. This is the only reason why I configured these features. Also, I haven't configured any VLANs or anything. This is all going to be in the default VLAN, which on Cisco switches is VLAN number 1. This is the configuration on fast Ethernet 00 on my R1, and as you can see, it's very, very basic. There is nothing going on there. And this is the configuration on gigabit 00 on my R2. The only thing that is different between R1 and R2 is this media type RJ45, and that is because my R2 has a dual media port. I can use either the fiber or the copper port, and I opted to use the copper, the RJ45 connector to my switch instead of using the fiber, which is not connected to the switch. So what I'm going to do now is I'm going to configure an IP address on my fast Ethernet 00 on R1, and I'm just going to use a very basic IP address 10.0.0.1, and on R2 I'm going to use 10.0.0.2 address. And what I'm going to do now is I'm going to ping between these two. This should generate some traffic, and I can see that actually it was successful. So let's go to Cat1 and see if Cat1 actually learned any MAC addresses here. If I do show MAC address table dynamic, I can see that I have in total 2 MAC addresses that have been learned. Of course, one MAC address here is on the port fast Ethernet 01, and the other one is in port fast Ethernet 02. So this one here is R1, and this one here is the MAC address of R2. So I can see that my learning actually worked. What I want to do next is I want to make sure that unless I generate some traffic manually, R1 and R2 don't speak, that they are absolutely silent. Now, you may be thinking to yourself, but isn't this exactly what is happening on the routers if you don't do anything? Well, it may or may not be. Let me show you what I mean. I do have another device connected to my network. This other device is a host running Wireshark, so the packet capture software. This is connected to Fast Ethernet 03 on Cat1. I'm going to use a feature on my Cat switch which is called the span, or the port mirroring really. And I'm going to monitor this port and anything that I receive on these two ports, I want to send a copy of this to my Wireshark so that I can actually observe all the traffic that enters these two ports in real time. Let me go and configure this feature real quick. So going back to the terminal here, I'm going to say monitor session 1 source Fast Ethernet to Fast Ethernet 2. So I'm going to capture the traffic from two ports, from Fast Ethernet 01 and Fast Ethernet 02. And I'm interested here, sorry, I am missing parameter here, interface. And I'm going to specify that I'm interested only in the received traffic. Then I'm going to take the copy of this traffic and I'm going to send it to the destination interface Fast Ethernet 03. And I'm going to bring this port up. So going to Wireshark, I can see here that I do have some traffic going on. Here I can see quite a few packets being captured. See, let me restart the capture just to show you this thing here. Actually, you can see them scrolling in real time. What I have here are the CDP packets. I also have the loopback packets. These loopback packets are really Ethernet keep lives. So I want to get rid of all this traffic and I want only the traffic that I generate to be present on this port. This is somewhat involved action. What I have to do is make sure that I turn off the CDP and I also have to turn off the Ethernet keep lives. And I have to do this on my R1 and R2. So going here to my R1, what I'm going to do on Fast Ethernet 00, I'm going to say no keep lives and I'm going to say no CDP enable. This turns off the CDP and also turns off Ethernet keep lives. I'm going to do the exact same thing on R2. So no keep lives and I'm going to say no CDP enable. With this configuration, what I should have now is, and let me restart my packet capture here, I should have relatively silent operation on my Wireshark. So I am not receiving any packets from R1 or from R2. Going back to my Cat1, I can observe my MAC address table here that I still have two dynamically learned MAC addresses. I'm still not receiving any traffic in my Wireshark. I'm going to clear my MAC address table. And when you clear the MAC address table here, you can clear the dynamically learned entries. So this is all gone. Now switch has to relearn all of these MAC addresses again. Okay? Going back to my Wireshark, still no traffic. R1 and R2 are not transmitting anything. What I'm going to do next is I'm going to turn off my monitoring. So now with this configuration, I have proven that there is no traffic coming from R1 and R2. And I can actually take a look at my dynamic MAC address table and I have nothing here. And I'm going to go to my R1 and I'm going to generate just a single ping. So 10.0.0.2, repeat 1. I'm sending just one packet. If I go to my Cat1, I can see that Cat1 has now learned MAC addresses from both R1 and R2. How did this process actually happen? How can we observe this process in real time? Well, let's take a step back. Again, let's clear the MAC address table dynamic and let's confirm that this dynamic table is empty. And let's enable the debug process. the debug command that I'm going to use is debug platform, and then I'm going to use the MATM feature, which is basically MAC address management information debugging. And here I'm going to debug the learning process. So now, as the switch learns the MAC addresses, I should be seeing the log messages in my terminal. Let's take a look. Again, let's confirm that we still don't have any dynamically learned MAC addresses. Going to R1 and sending single ping. Now we can see a lot of output here. What we are interested at this moment is that here we can see that we are adding a MAC address to our MAC address table. Which MAC address is this? How can I find out this information? Well, of course, I can do show MAC address table dynamic and correlate this information with the known information that I have here, or the information that I know about, or I can simply go to R1 and do show interface fast Ethernet 00 include hardware, and I will see what is the MAC address that is being used by R1. So here I see that this is the MAC address here, and we can see that this MAC address was first learned. What happened then is this traffic, this ping, was flooded because R1 knew where to send the traffic. How did R1 know where to send the traffic? Well, I did cheat a little bit here. Remember that I pinged, then I cleared the MAC address table, but then I pinged again? Well, when I first pinged, R1 actually learned where to send this traffic using protocol called ARP. It sent out the broadcast, R2 responded to this, so now R1 has this mapping. And this is very interesting because now we can see what happens on the switch when we have an unknown unicast traffic. How can I see that? Going back to my Cat1, what I'm going to do here now is I'm going to turn off my monitoring session. So I'm no longer going to send copy of any traffic to my monitoring station on port 3. I'm going to go to fast Ethernet 03 and I'm going to say spanning tree port fast. Again, the only reason why I'm doing this is to make things a little bit quicker. I'm also going to turn off the debug, and I'm going to clear my dynamic address table. So if I do show MAC address table dynamic, I'm not seeing anything because R1 and R2 are not generating any traffic. Going back to my Wireshark, now I can see some traffic going on here, and especially from the switch. So the only thing that I'm interested here is going to be the ICMP traffic. Okay? I only want to see the ICMP traffic. Let's restart the capture. So now on Wireshark, I'm going to be capturing only the traffic that is delivered on fast Ethernet 03 of type ICMP. So I'm going to go back here, still confirm that, okay, let's clear MAC address table dynamic. I'm still going to confirm that switch doesn't have any dynamically learned MAC addresses, and I'm going to send that one ping. So I'm pinging R2, which is connected to fast Ethernet 02. There we go. A single ping went out. And take a look at this. What I have here is on port number 3 on the switch. So on this port here, I have received a copy of the ping traffic sent by R1. Why did I receive the copy of this traffic? Well, let's imagine that, well, not imagine, let's observe what happened here. R1 generated an IP packet. We told it what is going to be the destination IP address. R1 also knew what is going to be the destination layer 2 address, the destination MAC address, and he knew that from our ARP table. So when this frame arrived to fast Ethernet 01, this was an unknown unicast frame as far as switch was concerned. What is an unknown unicast? It's the packet, it's the frame that has a destination MAC address that is not known in the MAC address table by the switch. So what does the switch do with this traffic? Well, it floods it. It's going to send it to all the ports on the VLAN except the port it was received on. So the copy of this traffic was sent to R2, but also a copy of this traffic was sent to our fast Ethernet 03 and hit our Wireshark. Now, let's send another ping. So here we can see that we had echo request and echo reply. The echo reply probably came before Switch actually managed to learn the MAC address from R1. But now the situation on Cat1 is slightly different. Now we have actually learned both R1's and R2's MAC address. So I'm going to repeat the process. No changes, no clearing on the MAC table, nothing. I'm sending the ping again. I'm still pinging R2. Going to my Wireshark, I can no longer see this traffic. No matter how many pings I actually send here, this traffic now is no longer being flooded. This traffic is now being sent only from R1 to R2. Why? Because Cat1 has learned the MAC addresses. It learned where it needs to send this traffic. And we were able to observe this process using debug platform MATM learning command. The next thing that I would like to show you is sometimes this behavior is not really what you want to have. Sometimes you don't want to deliver the traffic. You don't want to flood unknown unicast traffic. Is there a way to prevent the switch from flooding the unknown unicast traffic? Well, as it turns out, there is. It's a per interface command, and let's configure it towards our Wireshark station here. It's a per interface command which says switch port block unicast. Now, what this command is going to do is not going to block all unicast traffic. It's just going to block the unknown unicast traffic. So if I go out of my configuration mode, and if I go to show MAC address table dynamic, I'm still going to see that I have those two learned. Let me clear them up. So clear MAC address table dynamic, and I'm going to say show MAC address table dynamic, so I now no longer have any dynamic entries. Let's see what happens when I ping from R1 to R2. Before I do that, let me restart my Wireshark. So I'm going to restart the capture here. Again, capturing just the traffic that is delivered to fast Ethernet 03 on my Cat1, and if it's ICMP, I don't care about any other traffic. So going back to my terminal here, I'm going to go to R1 and I'm going to send one ping. This one ping is delivered to R2. On Cat1, here I can see that both fast Ethernet 01 and 02 have been entered in the MAC address table. And let's take a look at our Wireshark. Look, it's empty. There's nothing there. Why? Because unknown unicast traffic wasn't flooded to fast Ethernet 03. Let's make this even more fun. So going back to my terminal here, I'm going to configure this same command facing R2. So switch port block unicast. And I'm going to go to R1 and ping. I can see that I can still ping R2. No problem there. Let's clear the MAC address table. So I'm clearing the dynamic MAC address table. And there are no dynamically learned entries. And from R1, I'm trying to ping R2. Take a look. No go. Doesn't work. Let me show you the magic. So from R2 now, I'm going to ping R1, and that was successful. This first timeout here wasn't the result of blocking, it was the result of a missing ARP entry on R2, but that's not something that we are looking into right now. So now from R2, I was able to ping R1, and I was able to receive a response here, which means that show MAC address table dynamic now shows me that I actually have learned the MAC addresses here. And before I continue, let me correct myself, okay? I just realized that I made a small mistake. This lost packet here wasn't the result of a missing ARP entry. Of course it wasn't. It was the result of switch port block unicast. Why? Because there is a difference between theory and practice, okay? In theory, this is how things work. We send the traffic, and the moment the traffic arrives, the switch learns the MAC address, right? This is what the theory says. In practice, these things are not immediate. It takes time for things to happen. What happened here, the reason why we had this one dropped packet here that is highlighted, is that packet was sent, the frame was sent from R2 to R1. And when R1 responded back, when R1 wanted to send the frame back to R2, what happened is it happened before before Cat1 was able to update its dynamically learned MAC address table. So we didn't have an entry in the MAC address table when the response from R1 came. And we know that port facing R2 was configured to not allow this traffic. But then, in the meantime, between my first failed attempt and the second attempt, that update of the database actually happened. So R2 was able to ping next time. So now that I've corrected myself, and I do apologize for that slight omission there, going back here, the second ping was a success. So if I go now to R1, and if I repeat the ping that failed before, it's going to work like a charm. Why does it work now? Because now we actually do have this entry in the database. And if I take a look at the configuration of FastNet02, even though it was configured to block the unicast traffic, the unknown unicast traffic, this traffic is no longer unknown unicast. It is actually known unicast now, and it went through. So this is it about learning process on the switches. Let's take a look at how the packet goes through the switch. Which are the processes that frame or packet, call it whatever, undergoes when it goes through the switch. When we are talking about the life of a frame or a packet inside the switch, we have to examine two different operations that are happening on modern-day multi-layer switches. One is what happens with frames at layer 2, and what happens when we receive an IP packet that switch needs not to switch at layer 2, but actually route at layer 3. The functions that switch needs to perform are very, very similar in these cases, but somewhat different. Let's first look into the layer 2 forwarding of our frames. So at layer 2, let's say that we have a switch. So this is our switch. This is the entire switch that we are operating with. And switch has multiple ports, and we can receive and send traffic on multiple ports. Let's focus on one port only that actually receives the traffic. So let's say that here we have port number 1, and we are receiving a frame here. So this is layer 2 frame arriving here that needs to be forwarded through the switch and sent somewhere. What's the first thing that happens with this frame? Well, several tables need to be consulted. These several tables are security access lists. So let's write here security ACLs. Then we may need to perform certain QoS classification, and QoS classification on Catalyst switches can be done using different methods, but the one in particular involves use of the TCAM table, which are the QoS access lists. And then finally we need to consult the layer 2 CAM table, or our MAC address table. All these tables are going to be examined simultaneously. This is the power of the TCAM. Because you remember, in TCAM, we have those 134-bit long masks. And the whole idea there is that we can put a lot of information there, the source MAC address, the source destination MAC address, the source IP address, the destination MAC address, the destination IP address. All this information can go into these tables, and it can simultaneously be looked up from these different pieces of the table. Now, let's say that security access lists allow the traffic to go through. We have performed our QoS classification, and the layer 2 CAM table, the MAC address table, tells us what needs to happen with this packet. And there are two things that can happen when with the CAM table. One is we know exactly where to send our frame. Our frame needs to go to, say, port number 2, or needs to go to port number 3. And we've seen this before. This is part of our flooding process or forwarding traffic as unicast frames. Security access lists can either deny or permit the traffic to go through. So it's really just a binary operation. With QoS access lists, we are using those QoS ACLs to classify the traffic into different classes of traffic so that we can perform certain QoS operations. I'm going to talk about QoS separately, but for now, the first QoS operation that happens here inside the switch, when the frame has gone through the security access lists and QoS access lists and the CAM table, is we are encountering here first is the ingress queuing. Ingress queuing basically means that the frame is going to be sent into one of the multiple queues. How many queues are there? Well, that's heavily platform dependent. It depends on really how much money are you paying for your switch. You can have 2 queues, or you can have 4 queues, or you can have 8 queues on the ingress, and you can optimize the traffic as it is arriving to your switch from each port individually, or maybe you have shared ingress queues before that same frame is actually going to be sent to the backplane of the switch. So the first process here that we have is the ingress queuing. In ingress queuing, we are basically determining how are we going to send traffic to the backplane of the switch. What is backplane of the switch? Let me briefly go through that. When we have a switch here and we have multiple ports on the switch, how do we interconnect these ports? How do we get traffic from one port to another? What is the internal architecture of the switch? Again, this is heavily platform dependent. In some cases, we have very, very simple bus architecture, which is the equivalent of our thick yellow cable, where all ports connect to the same bus. This is not very efficient, and this is not commonly seen in modern day networks. Another relatively common architecture, actually, in less expensive switches is that we have kind of a ring structure, is that we have an internal ring to which ports connect here. So it's not a bus, it's a ring. So that frames actually can circulate, and you don't always have to send frames to everyone, because if frame goes from this port to this port, and let's say that we have a clockwise ring traffic direction here, this frame will actually just need to travel this far without actually affecting these 2 ports. Even more common architecture is to have redundant rings, or actually counter-rotating rings in our switches. What this means is that we can have a switch here, let's again go with 4 ports here, and we can have 2 rings. So this is one ring here, and the traffic here is moving in the clockwise direction, and we can have traffic here, another ring that moves in counterclockwise direction. And our ports would have connections to both rings here, like so. These are all internal connections. These are not external connections, just to clarify. So let's say that we had a frame that needed to go from this port here to this port here. We can send this frame this way, but if we had a traffic that needs to go from this port to this port here, we can actually send it using this direction here, again, without affecting this port in either case. On somewhat more expensive higher-end switches, we have an architecture that is called the crossbar. Now with crossbar here, what we have is kind of many-to-many connection. Imagine sort of a matrix of connections here back where our ports connect, so that no matter how many ports you have, you can dynamically build connections and interconnections between them. This is probably the most efficient transfer mechanism because you have any-to-any connection inside the switch. So when we talk about the backplane of the switch, we are really talking about any one of these architectures. It doesn't matter which one it is. It's just that when we talk about the queuing and when we are sending the traffic to the backplane of the switch, we are talking about sending it to one of these internal architectures. These are just simple examples. There are more complex ones. If on higher end platforms, if you have multiple line cards, you can have distributed forwarding architecture that actually line cards themselves have the copy of the CAM and the TCAM tables and the forwarding tables that are in use. So it gets a lot more involved what happens with the frame. But at this moment, just think about it in simple terms. Actually, not only in this moment here, unless you are doing heavy traffic in your network on your switches, these are the things that are not going to be too much of your concern in production networks, right? It's very easy to get lost in these internal architectures and spend too much time thinking about them, but you really need to focus on basics, understanding what happens overall in the box, and only if you're experiencing some sort of bottlenecks inside your equipment, only then start looking in these internal architectures. So here, the ingress queuing, after the ingress queuing, we are sending our traffic to the backplane of the switch. So let's write here that this goes to the backplane. Whatever it is it a ring, is it a bus, is it a crossbar, whatever it is, it goes to the backplane of the switch. Now, after the backplane of the switch, we need to send traffic out to one or more ports. Let's say that this particular frame here is determined to go out of port number 2. After backplane of the switch, we are sending the traffic to egress queues. Egress queues, similarly to ingress queues here, are designed to process the traffic before it leaves out of the port. So ingress queues are controlling how are we delivering traffic into the backplane of the switch to prevent the oversubscription of the backplane on the switch. And with the egress queues, we are trying to schedule to control the outflow of traffic as it leaves our switch and goes into the wire where it needs to be delivered. So here we have any number of egress queues. So let's call these egress queues. Now, how many egress queues are we going to have? Again, this heavily depends on how much you are actually paying for your switch. On lower end Catalyst switches like 3560 and 3750 switches, you have 2 global ingress queues, that is between all the ports before traffic goes onto the backplane, and each port has 4 egress queues. But I'll talk more about the queuing and these queues when I talk about the QoS. So finally, our frame arrives to the egress queue and is being sent out. Egress queue here is controlled by QoS processes with QoS schedules. So this is the lifetime of layer 2 frame. Let's take a look now at what happens with layer 3 packet as it goes through our switch. Obviously, the process is going to be very similar to the one that layer 2 frame goes through. So I'm just going to reuse the same drawing that we used, and I'm going to change it just a little bit. Now, when we talk about the layer 3 forwarding, it's important here to understand that what arrives here is not a frame, it's a packet. Now, the packet has layer 2 and layer 3 components of it. So what we have here is an IP packet which is encapsulated in layer 2 frame. Now, layer 2 information here, the important bit for our forwarding through the switch is the destination MAC address. The important information in the IP packet is the destination IP address. Now, destination IP address is end-to-end. which means that if I had a host A here that was connected to our multi-layer switch 1, which was connected to, say, router 1, which was connected to router 2, and here is our B. If I wanted to communicate between A and B here, when I send an IP packet from A to MLS1, and remember, multi-layer switch means that this really is acting as the router, this IP packet here will have the destination IP address of B, but it will have a destination MAC address of MLS1, as long as MLS1's address here was used as, say, default gateway for host A. So when the frame arrives here to our multi-layer switch, our layer 2 information is not really relevant here. This information here is not really relevant. We need to drop this information and look at the IP information that we have here. Now, based on this IP information here, we are going to perform a lookup in our table. Let me expand my switch just a little bit because I'm going to be needing some space here for one more table. The table that we are going to consult here at the ingress is going to be our layer 3 forwarding information base. On Cisco routers, the forwarding information base, sorry, not on Cisco routers, on Cisco switches, the forwarding information base is implemented in hardware using Cisco Express forwarding technology. It's a topology-based forwarding cache. Now, what do I mean by forwarding cache? Imagine when you have a routing table. It's basically a list of routes, available layer 3 destinations that the switch or the router knows about. And the information that we have there is what is the next hop information about for this route, and what is the egress interface. In other words, where do we need to send this packet if we were to send towards that particular destination. Now, when the ingress packet arrives to the router can go and consult the routing table and looks at, oh, okay, so I have the packet that goes towards this destination, I have to send it out of this interface, and this is the next hop. Okay, but what is my layer 2 information there? Which destination MAC address should I use? Oh, I don't have that information in my routing table. I actually have to consult my layer 2 forwarding table. So I have to go to the layer 2 forwarding table and find out, okay, for this IP address, which MAC address should I use? So it takes time, it's multiple lookups. The whole idea of Ceph is that this information is going to be compiled, it's going to be put into the cache information so that when the packet arrives, when we need to perform a lookup, instead of going to the routing table and based on the result from the routing table and looking up into the layer 2 forwarding table, we are going to do this all at once. We're just going to go to the Ceph table and ask, what do I do with this packet? And if the Ceph table contains the information what to do with this packet, we are going to get back the information. This is the destination, this is the outgoing interface for this packet, and this is the layer 2 information about it. In other words, I'm going to get the MAC address that I need to use. In Cisco switches, the Ceph works in conjunction with my layer 2 CAM table. So these two informations here, these two tables, they're going to be consulted simultaneously to get me the information that I'm going to use to perform packet rewrite function. Packet rewrite function is basically generating the new layer 2 header for the packet that I need to send. Let me explain that on my previous example here. When this packet arrived from A to my multi-layer switch 1, we have discarded this information here because the destination MAC address was that of MLS1. But I'm still keeping the information about destination IP address. I'm going to perform the lookup in my tables, and I'm going to get the information that my layer 3 next hop to reach B is R1's interface here. What I need to do is determine what is going to be the new destination MAC address for this packet here and insert that information in the packet that is going to be sent from MLS1 to R1. So I need to build the new layer 2 header on the IP packet that I'm sending. This is what the packet rewrite function does. From the packet rewrite function, we are sending the packet into the ingress queue. So this direct connection here that I had from the previous example does not exist. So everything else remains pretty much the same throughout the switch. From the ingress queue, we are sending the packet to the back plane of the switch, and you remember it can be a bus, it can be a ring, it can be a crossbar, multiple rings, whatever the architecture actually is on the back plane, goes to the back plane, goes to the egress queue, and the egress queue is processing and is finally sent out of the port. So that's it about the packet life inside the switch.